This conference will now be recorded.
Very good evening, students. We're back with the PYQ discussions. So today we had remaining questions from JEE Main 3rd December 2020. So we will discuss few more questions on this chapter, on this paper today. Let us start our discussions, and we can see the questions here. The first question is, two isolated conducting spheres S1 and S2 of radius 2 by 3r and 1/3 r have 12 microcoulomb and -3 microcoulomb charges respectively and are at large distance from each other. They are now connected by a conducting wire. Okay, they are connecting by conducting wire. A long time after this is done, the charges on S1 and S2 are respectively 6 microcoulomb or 3 microcoulomb. Then, or so these are the options given in this. We have to find out which one is the correct option here. So look, the situation is like this. So there is a sphere like this and another sphere. Okay, now it has charge 12 microcoulomb and this has charge -3 microcoulomb. They are separated by a large gap. Now if you connect this to the conducting wire, then what will happen, there will be charge. See here, there is a deficit of positive charges. Okay, here there is excess of positive charges. So you know what will happen. Suppose I have 12 electrons here. Just suppose 12 electrons deficit here, and there 12 electrons excess. So what will happen? See, the excess electron come here, and then what will happen? See, as a whole, the charge after connecting these two will be, see, 12 minus 3, 9 microcoulomb. As a whole, the charge will be 9 microcoulomb in both. Okay, now this charge, since these two had different radii, okay, see, this S1 has radius 2 by 3r, and you look, the S2 has 1/3r. As you know, the capacity of holding charge for a sphere is 4 pi epsilon naught, isolated sphere, obviously, like this. Okay, 4 pi epsilon 0 into r. That means C is directly proportional to r, right? So this one, see, after connecting, the total charge has to be 9 microcoulomb, but this will have greater proportion of the charges than this one. Okay, so they will actually, charge will be distributed over these two. The total charge is 9 microcoulomb, but distribution will happen according to their capacity. Since this has 2 times, see, radius, S1 sphere 1 has radius 2 times than this, then how the charge will be distributed? If I say the charge on the sphere S1 is Q1, then look, since their radius, see, if I write R1 is to R2, their radii will be 2:1, isn't it? So 2:1. So charge also will be distributed in this ratio. So I'll write 2/3 into total charge, that is 9 microcoulomb. So this will be 6 microcoulomb on this sphere 1, and if this is the sphere 2 charge, let us say Q2, this will be 1/3 into 9 microcoulomb. So this is how charge will be distributed on the spheres after long time. Okay, after long time, the total charge will be 9 microcoulomb, and that will be distributed according to their capacity. Okay, in proportionate to their capacity. So this S1 will have 6 microcoulomb. So this is the answer. Okay, 6 microcoulomb and 3 microcoulomb. I hope it is clear to you. I am not repeating again. Let us go to the next problem. So this problem is again related to capacitor. You can see this figure. So in the circuit shown in the figure, the total charge, see, total charge is given. So total charge is given means, suppose the charge is flowing through this circuit. Okay, charge is flowing through the circuit. So total charge flowing will be actually this much. Okay, and the voltage across C2, see, C2 voltage across C2 is 20 volt. That means what? The voltage 20 volt is across C3 also. This is same with this C3 also, right? Now the question is the charge on the capacitor C2. See, I know the voltage across C2, but I don't know what is the capacitance. Then how to find out the charge? It is very simple. Let us see the total charge. Since it is a continuous circuit, charge flows through the circuit will be same everywhere. So if this is 750 microcoulomb over here, so here also it will come up to here, say 750 microcoulomb. So that will be again 750 microcoulomb here also. Okay, the same charge, sorry, microcoulomb. So same charge will be flowing through the circuit. This is according to conservation of charge. Okay, charge is not going to be losing anywhere, it has to flow. So that's why we can say the total charge, see here the charge is actually distributed, sorry, gets divided into two parts according to the capacitance of this C2 and C3. So let us say, see, nothing to say, let us see here, if the potential difference across C3 is 20 volt, then what will be the charge Q3? What will be the charge Q3? Q3 will be C3 into this 20 volt. Okay, this much is actually the charge on the Q3. Then rest of the charge will be through C2. Okay, let me just do it here. 8 microfarad 10 to the power minus 6 into 20. That means, you know, this is 160 microcoulomb through this. Then rest of the charge will be on. So Q2 will be 750 microcoulomb minus 160 microcoulomb. I hope you are understanding this. Why I'm doing this? Because the charge, total charge, has to flow through the circuit. Okay, so here since this C2 and C3 are in parallel combination, so charge will be getting divided into two parts, C2 and C3, but finally they are, see here again it will be 750 microcoulomb, which is Q2 plus Q3, isn't it? So from here, if I know the Q3, then Q2 is 750 minus Q3. Okay, so this is what it is. So it will be actually 590 microcoulomb. Okay, so this is the answer. Now let us see the third question. It is very interesting question. Magnitude of magnetic field in SI units at the center of a hexagonal shaped coil of side 10 centimeter, 50 turns and carrying current I ampere in units of mu0 I by pi is. So the question is, see, this is a hexagon, suppose hexagonal shape coil. So hexagon has 6 sides, you know that, and each side has this 10 centimeter, and it is actually uniform hexagonal. Okay, uniform, or what to say, I think yeah, uniform word is fine. Uniform hexagonal, that means each angle, this angles also will be same, that means 60°. All right, the question is that current given I, current passing through each side is I, and each side has some 50 turns. Okay, 50 turns. So n is 50, I is I only, and see, let us say the sides A 10 centimeter, 10 centimeter. I can make it to meter also, doesn't matter. So 10 centimeter means 10 into 10 to the minus 2, so 0.1 meter. If required, I can make it. Okay, doesn't matter here. All right, so now the question is, what is the magnetic field at the center O? So this is the question. So they said you have to find out the magnitude of the magnetic field in the unit of mu0 I by pi. So this value I don't have to write. Anyway, so you look, this question is very simple if you know Weier's law. If you can apply Weier's law. So how to apply? See, this particular part was see, you have to just draw the hexagon, then you just target one arm or one side, and you calculate magnetic field for only one side. So how to do that? See, this AB, suppose one side, this has value A. If I connect this A and B points with the center, it will be a equilateral triangle. Okay, this will be an equilateral triangle. Okay, equilateral triangle. It will be an equilateral triangle. So see, each angle was 60°, right? See here, sorry, 6 into 120, each angle was 120, so it is divided by 2, so actually this will be 60, this will be 60, and also this will be 60. Okay, because these are AA, so obviously this will be these two will be same, so 60. So equilateral triangle has their angle 60°. Now see, I have to calculate magnetic field for this particular AB wire. See, this is conducting wire and finite wire. So for finite wire, we know, if suppose this length is small r, okay, small r, which I can calculate actually, small r. See, this distance from this point P, this is the perpendicular distance r, okay, from the wire. All right, so from the wire this point is at r distance away, so that is actually the height of the equilateral triangle, which is root 3 by 2 into A. Okay, A is 10 centimeter, we know that, we can find it out whenever required. So this is the R. Now you know what is the formula for a finite wire. You can recall, see, B is equal to mu0 I by 4 pi R into sine of theta 1 plus sine of theta 2. This is actually the formula. Now, which one is theta 1 and theta 2? So these angles you have to find out. So these angles are 30, 30, right? Because this is actually uh, perpendicular, which is dividing this angle equally. perpendicular bisector, I mean to say perpendicular bisector. So this angle theta and theta, both are theta and both are actually 30 degree. Now we can put this value r here. We have, say, I have to calculate the magnetic field in terms of, see, this is for only one, then the total magnetic field at the center will be six sides, and each side has 6 turns. So total current will be 6 into Ni. So here also I think I should mention here 50. The total current 50. So 650. So total magnetic field will be mu0 I by pi. Since this unit I have to calculate, let me keep this like this. So 6 into 50, okay, divided by 4r into sine of 30 plus sine of 30, which is 2 into sine of 30. Okay, if I do simplifications, let me do it here. I think I have some space here. Yes. So B total is going to be, so this actually 2 into sine theta means sine 30 means half. So 2 into half, 2 into half is going to be 1. So this particular part I can just leave. Mu0 I. Now I have mu0 I by pi. This is the unit. So 6 into 50, okay, divided by 4 into r. So this particular part I have to calculate actually. B total for r is actually root 3 by 2. A is 10 centimeter. So I can make that into meter. 10 into 10 to the power minus 2. Okay, this is the thing. And here it will be mu0 I by pi. 650 into 2 into 100. I'm just taking this to numerator. So I have 4 root 3 into 10. This goes like this. All right. So this, look, then what we get. So this mu0 I by pi will be there. So see, I get 500 root 3 mu0 I by pi. So this is actually in Tesla, obviously. So this is the actually magnitude of the magnetic field. Look, we had to find out in terms of mu0 I by pi and see the options. So option D will be the correct answer here. This is a very simple problem. If you know, see what is the bottom point here. This is the bottom point, and drawing this hexagon and getting this point, that this, if I join this adjacent like ends of the wire, a single wire, I'll get like to the center. If I add or connect the ends of a wire with the center, you will get actually a triangle, equilateral triangle. That point you need to know, and you need to know this formula for a finite wire. Okay, for a finite wire, what will be the magnetic field? Okay, all right. So I hope you are listening in background music, the nice Bengali music. I can't help because there is a marriage ceremony uh, neighborhood, so I can't help. You can actually go with this. Yeah. So let us concentrate on the numerical problem here. So an elliptical loop having resistance R of semi-major axis A and semi-minor axis B. So these are shown here. This is B, this is A. And this is the magnetic field, you can see placed in a magnetic field as shown in the figure. So magnetic field is actually, so if this is in the plane, XY plane, you can see that the magnetic field is along the Z direction, okay, Z direction. Okay, magnetic field is in the Z direction. That means this loop has area perpendicular to the magnetic field. Very nice. So the magnetic fields are actually penetrating perpendicular to the area. Okay, perpendicularly this area of the elliptical loop. If the loop is rotated by x-axis, see if this is rotated about x-axis with an angular frequency omega, then average power loss in the loop due to Joule heating we have to find out. See, first of all, what is power due to Joule heating? You know that this is power is actually I square R or V square by R. V means the potential or EMF uh, across the loop. Okay, so if you want to find out, or I can write E square by R, then I have to take the average of this. Okay, average power means I have to do this. But see, what is this R? R is actually a resistance which is given R. What is this E? E is the EMF developed due to the rotation of this. Because see, when we rotate this loop about x-axis, what will happen? There will be change in the flux. Change in the flux linked with the loop, and then there will be EMF developed across it. So I have to actually calculate that EMF, then things are easy. Okay, then life is easy. Okay, so this is the point here you need to understand, that the power loss due to Joule heating means this one, and you have to take the average of that. So how to find out EMF? EMF we know minus d phi by dt. For this, like see, whenever there is a loop rotating, how to write phi? How to get phi? Phi is B into A, right? B into A. But here, you know, always you have to write this in dot product. So B A cos theta, cos of theta. And this theta can be written as omega t. So ultimately, whenever there is a loop rotating, you have to write the flux as BA, B into area, B is the magnetic field, area B is constant anyway, and cos omega t. This is the thing you have to remember. This is actually here bottom point. How to write flux here. How to write the flux. Okay, how to write the flux? Whenever there is something rotating, you have to write BA cos omega t. Okay, you have to write BA cos omega t. Okay, now look, I can just do the derivative to get the EMF from here. All right, so if you take derivative, then cos omega t. Okay, just let me write this somewhere else. So I'll write this phi here. So BA cos of omega t. One more point here. So what is A? Area of this elliptical loop. You know, elliptical loop has area pi major axis into minor axis. This is the area of the elliptical loop. So I can actually write it here. Pi A B. Okay, this is nothing but A. So this is cos omega. So here these terms are actually constant. Only what is changing is this cos omega t. So now I can just do this derivative, ddt of pi a small b capital B cos of omega t. Okay, so here cos omega t means sin omega t, with omega multiplied with this, minus will come, so that minus will actually be making plus to this. So I'll get pi a b omega capital B, that is the magnetic field, and then I get sin omega t. Okay, this is actually the EMF. Now I have to find out E square. So E square will be whole square of this. So pi square, small a square, small b square, capital B square, sin square omega t. Now I have to take the average. See, if I take the average, so this is constant term up to this will be same. If I take average, this will be same. Only average will be for this, and also there will be r here divided by r. So sin square omega t. I hope you remember when we had learned time average in case of sinusoidal. Uh, in case of sinusoidal current, average power. How do we calculate? We calculate power in full cycle. So if you take average of this sine square cos square, it will be half. Okay, it will be half. So I'm not doing the integration. You have to do integration. Actually, if you want to take this sine square omega t, if you want to take average of this, you have to do this integration actually. 0 to t, and here dt here, and down there will be 0 to t dt. Okay, this is what you have to do. But after doing this, what we get is half. So if you take full cycle average of a quantity, see, if you take average of sin omega t in full cycle, this will give you 0. Cos omega t full cycle average will be 0. But if you take the square of those two, sin square, if you take average of sin square omega t or cos square omega t or whatever, cos square theta or sin square theta, then it will be half. So this average power loss will be pi square small a square small b square capital B square, then divided by 2r. This is actually the average power loss. So I hope this is the answer. So the first option will be the answer. Okay, all right, so let us go to the next problem. So here I'll just repeat once again. The bottom point is that how to write the flux, and how to find out the area of this elliptical loop. Other things are similar. And also one more point I have told you here, you may know also, so sin square omega t, if you take average of this will give you half. So this is the thing. Okay, all right, next problem. So this problem says a 750 hertz 20-volt RMS source is connected to a resistance 100 ohm, inductance 0.1803 Henry, and a capacitor of capacitance 10 microfarad, all in series. That means, you know, LCR. They are in series, and see there is alternating battery over here, so which is capable of sending RMS voltage of 20 volt RMS, and it has frequency this much hertz. This R is 100 ohm, This C is 10 microfarad, and this L is given as 0.1803 Henry. So you have to, so the time in which the resistance will get heated by 10 degrees centigrade is close to. See, obviously, when current will flow through this resistor, it will be getting heated up. And you know that formula, the heat generated will be H is equal to, I'll write Q. Heat generated in the resistor will be I square R into T. This we know, right? Now, the question is the time in which the resistance will get heated by 10 degrees centigrade from say 0, so suppose yeah, this is by 10 degrees centigrade, that means delta T. That earlier suppose the temperature was room temperature 30 degrees centigrade. Okay, now it has become maybe 40 degrees centigrade. So how long it takes to have this, okay, for the resistor? Okay, so I square RT, this small t you have to find out when the temperature change is 10 degrees centigrade and specific heat S is given. S is given 2 joule per degree centigrade. Okay, this is given. So it is very simple. Say we have to write M S delta T. You know that MS delta T. MS delta T is equal to I square R into T. Right? So this here delta T is given, S is given. Okay, so here mass of this, okay, since mass is not given, I can take some value 1 kg in inside it maybe. So let us take this as 1 kg. Okay, so we have to find out this actually. Okay, so ms delta t by I square r. Okay, I square r. So but how to find out this r? Actually this I has to be IRMS. So rest of the things are actually trivial. You can just do it here. See, IRMS is equal to VRMS divided by Z impedance. Okay, this is Z. So Z is again square root of XL minus XC whole square plus R square. So you have to put that. So if you put all those things, and R is again 10 ohm, say 100 ohm, and S you can put this 2J by 2J per degree centigrade. So this is actually this is not per month. I think this will take care of this M. Okay, this will take care of this M here, because this is 2 joule. In general, S is given as joule per degree centigrade per gram or per kg. Since this is given like this, for the resistance, it is already given. So ms, the total term is given as this. Okay, this is ms. Okay, so no need to worry about this mass. So ms I can put 2 joule per degree centigrade. Okay, for this resistance. So all the things are known. What I have to find out? I have to find out IRMS. Then you have to put it here. Okay, so it has little lengthy calculations, but very simple problem. If you do the calculations carefully, you should find out 348 seconds. I'm not doing the rigorous calculation here. So Z you have to find out, then the RMS by Z will give you IRMS. That you have to put here as a square. Okay, and this M in place of MS you directly write this one, 2 joule per degree centigrade. Okay, and delta T, what is delta T? Delta T is actually 10 degree centigrade which is given. Okay, then you will get in terms of, okay, so in terms of second you will get the value. All right, so we'll move on to the next problem. Okay, so this problem is very common problem, and at least one, like you can actually expect a question of this type in any competitive exam. Okay, at least one question you will be getting from electromagnetic wave chapter. This problem is given. So the magnetic field of a plane electromagnetic wave is given. See, this is given, B is given, this is vector. I should give vector 3 into 10 to the power minus 8 sine 200 pi y plus ct I cap Tesla. Okay, where c is given, c is actually 3 into 10 to the power 8 meter per second, which is the speed of light in air or vapor. The corresponding electric field vector you have to find out. So there are options like this. Okay, so you can see these are all k cap direction. Okay, so there are two things here. You have to find out the magnitude b0. So this is b0, right? You have to find out e0, otherwise things are all same inside. You don't have to find anything for the argument inside the sign. You have to only find out e0, then things are fine. Now so two things, one is magnitude e0 and another one is the direction you have to find out. Okay, so that's all. So what is the relation between this electric field and magnetic field? We know E0 is equal to CB0, or E by C is equal to B. That's what. So it is easy to find out what is E0. Okay, so E0 is 3 into 10 to the power 8, and see this is the B0. I have to multiply this 3 into 10 to the power minus 8. So this two will cancel each other, so you will get 9. So I have got E0. So you look here, then what I am getting, E is equal to E0 I have found out, so this is 9, then sine of 200 pi whole into y plus ct. Okay, this is along I sorry this direction I have to find out now. This is see, I have to find out what is the direction. I have found out the whole thing except the direction. I have to find out the direction. So to find out the direction, you need to know in which direction this wave is propagating. In which direction this wave is propagating in the given equation, this magnetic field is propagating. Sorry, magnetic field is oscillating in the y direction. Sorry, I direction, that is fine. But along which direction the whole electromagnetic wave is traveling? We know a standard equation will be A sine omega t minus kx. Okay, so this is actually moving along positive x direction. Okay, so if I write omega t minus ky then it is positive y direction, traveling along positive y direction. So I have to actually see the direction from the argument in the argument of the sound sign. Okay, so I have to see the argument how it is. So in this case, you look, this y has a positive sign. When it is positive, that means it is actually moving in the negative y direction. So it is moving in the negative y direction. So the whole wave is moving in the negative y direction. Now, I hope you are understanding. So you have to understand first along which direction the whole wave is traveling. It is in the negative y direction for this case. Now see, I know the direction of propagation can be found out by taking the direction, multiplying the direction of E cross B like this. E cross B is proportional to K. Okay, at least direction wise, there will be some factors here. So K is the propagation vector. Okay, propagation vector, that means the direction of propagation of the whole electromagnetic wave. Okay, so E cross H I have to see. So when it is minus K cap, then, and also this is I cap, then what should be here so that you get minus K cap. So I, J and K. I can go with the cyclic rule. So I have to get K. That means you have to multiply minus K means J cross I. Okay. J cross I you have to multiply. Okay. J cross I you have to multiply. Oh, I see. This is Y direction. I'm sorry. It is propagating along minus Y direction. I see. See the, okay, K vector, it is along minus K. Okay, K vector along minus Y direction. I'm sorry, it is along minus Y direction. So I have to get minus J. So what should be this? Okay, what should be the direction of the electric field such that I get minus J? So you should get minus J. So this is K. K cross I is actually minus J. K cross I is minus J. Okay, K cross K cross I. Okay, K cross I will be minus J. Sorry, this is K cross I j K. So it will be positive, but if I give minus here, then I get minus. I don't know whether you are getting confused. Let me just go here. Okay, so let me just uh, explain here once again. See, it is very easy to find out what is the magnitude of the electric field, as well as you can find out this expression also, except the direction. To know the direction, you look this argument in the given magnetic field. So here I can see that K vector is along minus J cap. Okay, that means the whole electromagnetic wave is propagating along negative Y direction. So I know the direction. See, this is I cap. So B is oscillating along I cap direction. Okay, so to get minus J, this electric field vector had to oscillate in the minus K direction. Okay, this is what was the analysis. So option B will be correct answer. Just look, this there should be minus sign here, and here it is K cap. Okay, look this option B. Okay, I hope it is clear to you. All right, so see, this type of problem will be very easy, you know, if you know this relation E by E0 by C is equal to B0, this one, and this relation, the direction of propagation of the wave will be found out from E cross B. Okay, this is actually proportional, but direction wise I can write this. So these two things you have to Like these two things you have to remember. Okay, and from here, and also you know the cyclic rule. Okay, so you can actually analyze from here. And one more point, as I said, you need to know the like standard format of expressing any wave. Okay, so from seeing the, like by seeing the wave equation, you should be able to say in which direction the wave is traveling. Okay, so these are the points. Okay, this is from wave optics. In a Young's modulus, sorry, in a Young's double slit experiment, light of 500 nanometer is used to produce an interference pattern. When the distance between the slits is given is this 0.05 millimeter, angular width of the fringes formed on the distance screen. Look, the question is, this is double slit S1 and S2. This is the slits and this is the distance screen. So there is a distance between them, slits and the screen as distance D. Okay. Now say the light used is given, that is 500 nanometer, and this A slit widths are actually given A. Okay, slit width is given A. Sorry, slit width D is equal to, or A, whatever it is, D is equal to given. Small d generally we take in case of Young's modulus, sorry, Young's double slit experiment. Just excuse me, whenever I say Young's, then modulus will come automatically, but this Young, I don't know whether this Young and that Young of the modulus are same or not. So, but Young's double slit experiment, it is different than Young's modulus anyway. So D is given capital D. Okay, capital D is not given anyway. All right. So what is the question? Question is when the distance between the slits D is this 0.05 millimeter, the angular width in degree you have to find out. Angular width of fringes formed on the screen. See, to find out this angular width, so you need to know what is the linear width. Linear width means fringe width. Okay, you need to know fringe width. Suppose there is fringe width of beta. Okay, you know the fringe width is beta here. So now you can find out angular. So this is the theta. This you have to find out. Okay, so this is parallel. Okay, this is D, this is beta. So you know this is tan theta is equal to, or this angle, theta angle will be very, very small anyway. So this will be tan theta nearly equal to theta, that is equal to perpendicular beta by base, this is D. Okay, so you have to remember this, the theta is equal to beta by, so angular width of interference fringe will be beta by D. And beta is what? Beta is d lambda, capital D into lambda by small d. This is beta, and beta is, see, capital D is down again. So this is the one. So you can directly remember the angular width is lambda by small d. This is the expression for the angular width. Okay, if you can remember it is very fine. Otherwise, you can just come from beta by d. Okay, this is the real expression. All right, so angular width of the interference fringe we have found out. Now we have to put the values and find out what is the theta. Okay, let us do the calculation. So theta is lambda by small d. Lambda is how much? 500 nanometer. So I will write to 10 to the power minus 9 meter. Here 0.5 into 10 to the power minus 3 meter. Okay, So here another 2 is there, so I can write here 10 to the power minus 5, and 5 I can make this 5. Okay, so what we get here, this will be in radian actually, rad. Okay, then so what we get here 100, and this will make, this will be actually to minus 2. That means 0.01 rad. Okay, so we know pi rad is equivalent to 180 degree. So 1 rad 180 degree by pi, then 0.01 rad. Okay, so you have to multiply here 0.01. So if you do the calculation, you will get nearly 0.57 degree. Okay, so the first option is the correct answer here. Let us go to the next problem. So what was the bottom point here? You need to know what is the expression for the angular width of. So let me write it here. This is angular width of, this is actually angular width of interference planes. Interference planes in, okay, in Y Young's double slit. Okay, YD double slit experiment. Okay, so let us go to the next problem. So this problem is from modern physics. When the wavelength radiation falling on a metal, it changed from 500 nanometer to 200 nanometer. The maximum kinetic energy of the photoelectrons becomes 3 times larger. The work function of the metal is. See, this is from photoelectric effect. So we know Einstein's photoelectric effect says the like equation of Einstein's equation for photoelectric effect is maximum kinetic energy K is equal to the energy of the radiation. We can write h nu or h by lambda, since lambda is given, so h by lambda minus work function phi. This phi is actually work function. Okay, work function. This is the energy of incident radiation. Incident radiation. Okay, so the wavelength, it changed from 500 to 200 nanometer. Then this kinetic energy becomes 3 times larger. That means I can write, if this is K1 for AC by lambda 1, phi is always constant for a metal surface. Then I can write K2, which is actually 3K1 is equal to HC by lambda 2 minus phi. I hope you agree with me according to the given question. Okay, I can write this. Yes. All right. Now I can put this K1 here. So 3 into HC by lambda 1 minus phi. This is HC by lambda 2 minus phi. So I have to find out actually phi. So let us take this phi to this side. So it will be 3 phi minus phi, and this will be HC by lambda 1 Yes. So AC by lambda 1, AC by lambda 2. Okay. I'm sorry, this, I think there will be 3 here. 3 AC by lambda 1. Okay. So, all right, let me just see. I just go here. So I get pi 2 pi is equal to 3 AC by lambda 1 minus AC by lambda 2. I have see options are given in electron volt, so better to know what is the value of AC in electron volt. This is 1.23 something into 10 to the power minus 6 electron volt. If you require, you can use that. Now, see this AC, let us take common AC. Then it is 3 by lambda 1 is 500 minus this is 1 over 200. So AC into this is LCM 1000. So this is 6 minus 5. Okay. So this will be again, it is in actually, since this is nanometer. Okay, let me see, this is actually in nanometer. Okay. So there will be nanometer down. Okay. I can write AC by 1000 and 10 to the power 9 here. This is in nanometer. Okay. Now look, if I put the value of this AC, what we get 1.23 into 10 to the power minus 6 electron volt. This is meter. Okay. So here I have to find out pi. So 2 down. Okay. So there will be 1000 and there 10 to the power 9. Okay. So this actually will cancel and you will see it will be nearly 0.61. Okay, so this is in electron volt. I hope this will be given in your question, this AC value in terms of electron volt. If not, then you write 6.63 into 10 to the power minus 34 and this 3 into 10 to the power 8 meter, then meter per second, and then you divide this to get into in electron volt. Okay, this will help you. Otherwise you have to remember this value AC 1.23 into 10 to the power minus 6 electron volt. Okay, so this will be the answer. All right. Okay, so this is question, I think this is the last question. When a diode is forward biased, voltage drop across the diode will be, or across the junction will be 0.5 volt. The safe limit of current through the diode is 10 milliampere. The battery EMF is, if a battery of EMF 1.5 volt is used in the circuit, the value of the maximum resistance to be connected in series with the diode so that the current does not exceed the safe limit. Let me draw the circuit diagram. So this is a diode. Suppose this is in forward bias, then voltage drop across this diode is actually 0.5 volt. Now you have to use a resistance across this, like in series with this, when you have connected a battery, DC battery, say DC battery of 1.5 volt, and maximum current it takes, maximum current through the circuit should be 10 milliampere. This is very simple, you know, very simple to find out this. Say, since this is the drop, then the effective potential which will actually drive the current in the circuit will be 1.5 minus 0.5. And what is the current then? This is the effective voltage divided by R will be the current, and that is given as 10 milliampere, 10 to the power minus 3 ampere. This was actually very easy question. So R will be 1 divided by 10 into 10 to the power minus 3. So if I just take to here, this is 1000 here, this is in ohm, so this will be 100 ohm. Okay, 100 ohm resistance. Okay, this is the maximum resistance you can use, so that the current through the circuit will not cross the safety limit. Okay, so 100 ohm. So this is all for today. We have some more remaining questions in this paper. We'll take up these questions tomorrow. Thank you for your patience. Bye for today.